Okay, the subject of this lesson is nuclear fission. We've looked at nuclear fusion, we've looked at how fusion is used in stars, so we need to just look at what we mean by nuclear fission. People often get confused between nuclear fission and nuclear fusion. You must be careful that you don't misspell either words and that you know the difference between them. So you've got to know what fission is, you've got to know how fission is caused, what this thing called a chain reaction is, which is how nuclear fission goes on and continues, and then also at the end we're going to link fission to electricity generation and using it in a power station. So the word nuclear fission just simply means to split up. And it's used in two ways. It's been used by humans in bombs in an uncontrolled fashion, and it's used in power stations in a controlled fashion. So what is nuclear fission? If we just have a look on a nuclear level, hence the term nuclear fission, if you take quite a large nucleus, such as here we've got uranium-235, and if you can get that to absorb an extra neutron. So here we go, we can see the uranium-235 has absorbed a single neutron, so the number the mass number of uranium has gone from 235 to 236. And what happens on a nuclear level, this causes the nucleus to become quite unstable. So rather than staying unstable forever, it sort of deals with this by splitting up. And there you go, there's a sort of a big flash on the animation there, and this is split up into two separate nuclei, both of different elements. You don't have to worry about learning which elements it splits up to, you'll always be given that or told that. So this example has gone into these two in a second, we'll look at a separate example. But here, the main idea is that a single nucleus of uranium absorbs a neutron, has been split up into two different elements, but also along here you can see that there are additional neutrons left over, and these are released as well. So if we look at this in terms of an equation, this would be an equation. So here again we've got uranium-235, it's absorbed a neutron. So this is how we'd write down a neutron. It's got a proton number of 0 and it's got a mass number of 1, hence it's a neutron. And it's absorbed it, it's split up, and this sort of spark here, this flash, is showing us that energy is given off, and it's fissioned, or it's split up into this new nucleus, which is cesium with 55 protons, this nucleus, rubidium, that has got 37 protons, and we've got two neutrons left over. And again, you don't have to learn these equations, you just need to be happy to maybe fill in some blanks. So the couple of questions to have a look at: what do you notice about the mass numbers in the above equation, and what could the additional neutrons go on to cause? So if you added up 235 plus 1, on this side of the equation we've got 236, a mass number of 236, and if you add up 140 plus 94 plus 1 plus 1, you'll also end up with 236. So the total amount of mass on this side, or the total amount of protons and neutrons on this side, equals the amount of protons and neutrons on this side. We haven't lost anything. In the rearrangement of this, we have released energy. The question here as well is, what could the additional neutrons go on to cause? And we're going to look at that now by considering what we mean by something called a chain reaction. So what is a chain reaction? Here, if we look, we're going to sort of start again. This is our uranium nucleus. It's absorbed a neutron and it's split up, like we've seen. Energy has been released, and we've got these three spare neutrons. Now these three spare neutrons can go on to be absorbed if there's three other uranium nuclei present, just like you saw then. Those three spare neutrons would go on to be absorbed by more uranium nuclei. They would split up, leaving us with more neutrons, and then these neutrons could also be absorbed by more uranium nuclei that would also split up and end up with more neutrons being produced. So if we just go back, you can see we start off with 3 neutrons. So the first fission causes 3 neutrons. Those 3 neutrons go on to cause 3 more fissions. There they are. Those 3 fissions produce 3 neutrons each, which is 9 neutrons, and those neutrons go on to cause 9 fissions, each producing 3 neutrons, which would go on to produce 27. So you can see this process can really gather pace very quickly. It goes from being controlled, you might think initially it's controlled, but after 2 or 3 or 4 phases or stages, it rapidly becomes uncontrolled. So how would we use fission? Well, in a nuclear power station, you might remember this diagram from core science. Here we've got a power station where we've got a boiler where some water is going to be boiled, and we'll see what happens in a second. But rather than coal heating the boiler, here we've just got a nuclear reactor. So if we just get our nuclear reaction going, this would be a fission reactor, and inside here you'd have uranium, a nuclear fuel that is being split or fissioned. The energy is released in the fission process, as we've seen. That energy is being used to heat up the water. The water is heated up to produce steam. The steam is allowed to travel down pipes under high pressure to turn a turbine. The turbine turns a generator, which produces electricity to go into the national grid to get sent to our homes and factories and businesses, etc. So this is pretty much exactly like a coal-fired power station, apart from this little bit here. Going back to it, if we think, well, how on earth do we have a fission reactor that remains under control and doesn't go out of control and a huge chain reaction continues to occur and goes on and on and on? Well, we need to do something with the neutrons. The reason we put this in this lesson is the fact that sometimes exam questions might get you to think about a nuclear reactor, because this is our main application of nuclear fission. So if we need to get rid of this uncontrolled reaction, the thing we need to probably get rid of, if we could get rid of some neutrons, then the less neutrons that are there to split up more and more uranium nuclei, we would be able to keep this reaction under control. This is done by something called control rods, and control rods are made of a substance called boron, and boron's very good at absorbing neutrons. So it takes neutrons out of the chain reaction. So rather than having 3 neutrons producing 9 neutrons producing 27, you can quite literally just keep it so that you've just got a steady reaction where one fission releases 1 neutron, and that 1 neutron goes on to produce 1 more fission, and so on and so on. And so these control rods on this diagram, these are the black lines, these are the control rods. These would be lowered into a nuclear reactor. This is a little simple diagram of a reactor. You can see where the fuel would be in this yellow box. This is where the fission's taking place. So these control rods will be lowered down and absorb some of the neutrons so that they stop or slow down the chain reaction.